Hello, this is a continuation of lesson 4.8. Last time we defined the concept of the kernel and the range of a linear transformation. The dimension of the kernel is called the nullity, the dimension of the range is called the rank. Today we will put those two together in the rank-nullity theorem, also known as the fundamental theorem of linear algebra. So if we have a linear transformation T from vector spaces U to V, then the dimension of the kernel of T plus the dimension of the range of T is equal to the dimension of the domain of T. So this equality here is called the rank-nullity theorem because the dimension of the kernel is also called the nullity of T. The dimension of the range is also called the rank of T. The domain of T is obviously just U, so this is the dimension of U. You may have noticed in the exercises for last section there were a lot of problems where you had to calculate a basis for the kernel and a basis for the range. If you go back and count the number of vectors in those two bases, you will see that they always add up to the number of vectors that you would need in the domain, the dimension of the domain. So to prove this theorem, we're going to assume that the dimension of the kernel is some quantity m, and that the dimension of the domain is n, and then we'll prove that the dimension of the range has to be n minus m. So we're assuming that this quantity here is m, this quantity here is this dimension of the domain is n, and we want to prove that the rank is n minus m, which will prove the theorem. So let's consider two bases here. So the bases u1 to um. A basis for the kernel because it's dimension m, so there are m basis vectors. The kernel is a subset of U, which means you have to add a few more vectors to get a basis for U. So we're going to start with the same vectors u1 to um because these already span the kernel and they're linearly independent. And we can just add as many more as we need in order to span the entire domain. So we're going to continue after m to m plus 1 all the way to un. So now we need to prove that a basis for the range has n minus m vectors. So let's start with proving that we have a set that spans, and then we'll prove that that set is also linearly independent. So we'll take an arbitrary vector u in the domain. We can write it in terms of the basis vector for u. So we can write it as a1u1 plus a2u2 all the way to plus am and then keep going am plus 1 um plus 1 all the way to an. So now we're going to take the image of this vector, so t of u is t of this whole vector right here, and because u is assumed, or the transformation is assumed to be linear, we can use the properties of linear transformations that preserve addition and scalar multiplication to move this t in front of all of the basis vectors, a1t, u1, etc., plus am t, um, plus am plus 1 t, plus 1, all the way to plus an t, un. Okay, so now we see that all of these vectors tu1 through tum are all 0 because we assume that the vectors u1 to um are all in the kernel, which means their image is 0. So this first part of this expression will be equal to 0. So what we're left is just the second part right here. Because this vector t of u is completely arbitrary in the range, we see that here we have a set that spans the range. So the set of vectors t u m plus 1 through t of un spans the range of t. So now we want to show that the same set is linearly independent. So for this we need to consider the equation, we'll call this bm plus 1 tum plus 1 plus all the way to bn tun equals the 0 vector. This is the equation that we use always to show whether something is linearly dependent or independent. We're using the basis or the vectors that we had in this set right here. Again, because t is linear, we can use the linearity of t to rewrite this as t of bm plus 1 um plus 1 plus all the way to bn un equals 0. So now we see that this large vector that we have written in here actually is in the kernel of t because its image is the 0 vector. Because it's in the kernel, we can write it in terms of the basis vector for the kernel, u1 to um. So we can write the vector bm plus 1 plus 1 all the way to plus bn un as some linear combination of the basis vector for the kernel. So we can call this c1 u1 plus all the way to cm um for some c1 to cm in R. So moving all these terms to the right, we obtain c1 u1 plus all the way to cm um minus bm plus 1 plus 1 minus all the way to bn un equals the 0 vector. So these vectors that we wrote right here, u1 to un, are a basis for u as we assumed up here. Which means that that set is linearly independent. That implies that all of these coefficients have to be 0 in order for this equation to be satisfied. So c1 and c2 and all the way to cm and the bm plus 1 and the bm plus 2 all the way to the bn must equal 0. This is the only solution. Only solution to this equation that we had written up here. And this includes all the b's. All the coefficients that start with a b must be 0 in order for this equation to be satisfied, which shows that this equation right here has a unique solution, and that shows that the set that we had considered up here to span the range of t is also linearly independent. So t of u m plus 1 to t of un is linearly independent. So now if we take these two parts together, the conclusion that this set spans the range of t and that the same set right here is linearly independent. Together we have found a basis for the range and there are n minus m vectors in this set. Therefore, the dimension of the range is n minus m, and that's what we needed to prove the rank-nullity theorem. So the rank-nullity theorem is completely general and universal for any linear transformation from any vector space to any other vector space. But it's used very much for transformations from Rn to Rm. That is a special case of the rank-nullity theorem, which we'll see right now. So if we take a linear transformation from Rn to Rm, so in this case, T is also a matrix transformation. Which means you can write it as T of some vector u in Rn is equal to a matrix A times u, where this matrix A is called the standard matrix of T. And it has size m by n. So in this case, if we want to find the kernel and the range of this kind of transformation, so first the kernel of T. So this is the set of all the vectors that map to the 0 vector in Rm. So it's all the vectors u in the domain Rn, such that AU equals 0. So you see, in order to find the kernel, all you have to do is solve this homogeneous system, and the solution will be the kernel. So therefore, the dimension of the kernel is the number of free variables that you obtain when you solve this homogeneous system. Number of free variables in this solution set. which, if you solve this using Gaussian elimination, ends up being the number of columns in the row reduced echelon form of A that do not have a leading one. Those are precisely the variables that end up being free variables when you write the solution set. So, second, we can find the range of T. So we can write the same transformation right here. So T of U, which is A times U, we can break down this into a linear combination of the columns of A. So C, or U1, C1 plus U2, C2, all the way to plus UN, Cn, where these vectors C1 to Cn are the columns of A. So if we write this transformation using this form, you see that the range is the set of all the images, which is a set of all the linear combinations of the columns of A. In other words, the column space. So the range of T is a set of all images. Of the vectors in the domain, which is the column space of A. Therefore, the dimension of the range is the dimension of the column space of A, which is the rank of A. So you see that the dimension of the range being the rank is what explains why the word rank is used for the case of a general linear transformation. And the rank of A, if you remember, is a number of columns in the row reduced echelon form of A that have a leading one. So, therefore, the rank-nullity theorem in this case so you have the dimension of the kernel of T plus the dimension of the range of T, which we now know is the rank of A, is equal to the domain, the dimension of the domain. The domain is Rn, so its dimension is simply n, which is the number of columns of A. Which can also be verified because the dimension of the kernel is those columns that do not have a leading one in the row reduced echelon form, and the dimension of the range is those columns that do have a leading one in the row reduced echelon form. Therefore, the sum of the two is just the total number of columns of A. So to illustrate this theorem, we'll just repeat one of the problems that was assigned for last lesson. A linear transformation from R3 to R2, defined as T of a vector in R3 ABC equals the vector in R2 A plus B plus C and 2A plus 3B minus C, which can be written as a matrix transformation where the standard matrix is 1, 1, 1, 2, 3, negative 1 times the vector ABC. So this is the standard matrix A of T. So to find the kernel, we want to find all the vectors such that all the vectors a, b, c that map to the 0 vectors. So we want to solve this equals the 0 vector. Which can be done by Gaussian elimination. If you take this matrix and make it into an augmented matrix, and put that augmented matrix into row reduced echelon form, so this ends up becoming, in row reduced echelon form, 1, 0, 4, 0, and 0, 1, negative 3, 0. So in other words, we have a plus 4c equals 0 and b minus 3c equals 0. So we can take c to be the free variable, r, in this case b becomes 3r, and a becomes minus 4r. So we have the kernel is a set of all vectors r times the vector minus 4, 3, 1, where r is a free variable. So we can find a basis for the kernel. It's a basis that has a single vector, minus 4, 3, 1. So we see that the dimension of the kernel is 1. By the way, if you look at this row reduced echelon form of the matrix, you see that there's only one column that does not have a leading 1 in it. And so that matches the dimension of the kernel. The other two columns have leading 1s in them. So now for the range. So we know that the range of T is equal to the rank of A, or the dimension of the range is the rank of A. And the rank of A is the dimension of the column space, but it's also the dimension of the row space. Which is equal to 2, the number of columns in the row reduced echelon form of the matrix A that do have a leading 1. Therefore, we know that the range of T is a subspace of R2 of dimension 2. So the range of T is actually equal to R2. So a basis for the range of T is just a basis for R2, so you can choose, for example, the canonical basis for R2, 1, 0, 0, 1. And the dimension of the range of T is therefore 2. You can verify the rank-nullity theorem. The dimension of the kernel is 1, the dimension of the range is 2, the sum is 3, which is the dimension of the domain, R3. Finally, the rank-nullity theorem for transformations from Rn to Rn is extremely useful to determine existence and uniqueness of solutions of linear systems, like we did a few sessions ago. We can even go further now that we have the rank-nullity theorem. So, for example, let's consider a linear system AX equals B, where you have 13 equations and 14 variables. And let's assume that a solution always exists. For all vectors b. And so the question that we may want to ask here is, if we replace this vector b by a zero vector, which makes it a homogeneous system, ax equals 0 for the same matrix A, does this have non-trivial solutions? So for that, we need to find what the kernel of this transformation is. So first of all, to find the answer to this question, notice that the matrix A is a matrix that has 13 by 14 in its size, so it can be seen as the standard matrix of a transformation. That goes from R14 to R13. So solution always exists. That means that the column space of A is equal to R13. Therefore, we have the rank of A equal to 13, so it's a full rank matrix. So now we know from the Rank-Nullity theorem that if the rank is equal to 13, therefore the dimension of the kernel is equal to 1. So 14 minus 13, 14 being the number of columns of A. This means that the system AX equals 0, when you find its solution, will have one free variable. Therefore, non-trivial solutions do exist. So the trick here is using the Rank-Nullity theorem to find the dimension of the kernel, since you know the rank. You can also use the Rank-Nullity theorem in the other direction if you know the kernel to find the rank of the matrix, and get information about existence and uniqueness of solutions in that scenario as well.